Oh. Welcome to our video about function of several variables. These are the functions which depend on more than one variable. For example, the volume of a circular cylinder, we have its formula V equal to pi r square h. In this case, the r and h, which are the radius and the height of the circular cylinder, are the two variables. But before we go into detail about functions of several variables, let's take a look at the function of single variables. So a function y equal to fx is a function of single variable. So we can see that y actually only depends on one variable, which in this case is the x. And its domain, in this case, we can say that is the set of all possible x values, or in other words, the set of all inputs. The range will be the set of all possible y values, or the set of all outputs. And the graph will be the set of all possible points xy produced by the function. And geometrically, we know that it is a line in space, whether it is a parabola, hyperbola, a straight line, etc. Here we have some examples of functions of single variable. First of all, we have y equal to cos x. Its domain is all possible real numbers, and its range is from -1 to 1. Let's look at its graph. So here is the graph of y equal to cos x. So we see that the range is from -1 to 1, and the domain is any real numbers. Even if we try to make the interval larger and larger, the range is still the same, from -1 to 1. Okay? And the x values goes to infinity. Secondly, we have y equal to ln x. Its domain is between 0 and infinity, and its range is between -infinity and infinity. Let's take a look at its graph. So this is the graph of y equal to ln x. Notice that this part of the graph goes down to -infinity, and this part of the graph goes up to infinity. You might think that this part of the graph may eventually levels out, but this is not the case. As the x value increases, the y value increases as well, although it's a small increment. Lastly, we have y equal to square root x. Its domain is the set of all real numbers from 0, and its range is the set of all real numbers from 0 as well. Let's take a look at its graph. So this is the graph of y equal to square root x. We see that it starts from 0 and goes up to infinity.
Alright, so that's all for the function of single variable. Now let's look at the heart of our lesson today, functions of multiple variables. Indeed, in real life, lots of formulas in physics or chemistry or any other academics requires a lot of variables instead of just one. So let's just start with the basics here. Let's start with functions of two variables. So what is a function of two variables? It just means that it's a function that can be represented in this form, z equal fxy. And what about the domain of this kind of function? Well, the domain of this kind of function is the set of all possible xy values. And the range is the set of all possible z values. And the graph of this function is the set of all possible points x, y, z produced by the function. Or you could interpret it as a surface in space. So here we list some examples of this kind of functions. So notice that all of these functions right here have two variables x, y listed in here. This is the signature of a multivariable function, or more definitely the two variable functions. So what we're going to do now is to find the domain and range of these kind of functions. So let's figure out the domain and range of the first example, z equals to cosine of x multiplied by the sine of y. So what exactly is the domain again? Well, the domain is just the set of all possible x and y values. What do you mean by that set of all x and y values? We just mean that what exactly are the numbers that we could plug into the x and y here? Or in other words, what exactly are the numbers that we can plug into here so that this function makes sense? Well, if you want to make sense of this function, we have to find if cosine of x and sine of y makes sense, because if one of them doesn't make sense, then it's just like one number times something that is undefined. It's just impossible. So to find that, we have to separate them. So we let p equals to cosine of x and q equals to sine of y, and we do it alone. So what numbers that we can plug into cosine of x, which would make sense, which would make this function p make sense? Well, any values can be represented inside this x. I mean, we can plug any numbers into x. So the domain under p is the set of all real values, right? And this goes to the function q here too. So if all the numbers are represented inside here, and remember again, what is domain? The domain is the set of all x, y values. Well, we know that the set of all x, y values are all the real numbers. So we could conclude that the domain for z is all real numbers of x and y. So what's the range of this function right here? Well, what's range again? Range just means what's the set of all the possible z values that z can take. So how do we find that out? Well, notice that z is defined by this two function right here. So in essence, what the range of cosine of x will and the range of sine of y would determine what z values can take, right? So let's just list out what the range of cosine of x and sine of y are. So the range of cosine of x, is just from -1 to 1, right? And the range of sine of y is just, again, the same thing, -1 to 1. Alright? So how do we find out the range of z given these two ranges? So what we could do is try to take the minimum value that cosine of x could take and the minimum value that sine of y could take, and when we multiply together, maybe it could give us the minimum value of z. So let's just try that. So if cosine of x is -1 and sine of y is -1, if we multiply both of them to each other, we would get 1. So possibly the minimum value that z could take could be 1. But let's just plug in some other values. Let's just assume that if cosine of x is the maximum value, that is 1, or sine of y to be the maximum value, that is 1, if we multiply both of them together, we'll also get 1. So does that mean that the range of z is equal to 1? Well, you have to recall that the variable x and y are independent of each other. What do we mean by independent of each other? It just means that x and y doesn't have a relationship with each other, so they could take any values. In other words, the range of cosine of x and the range of sine of y could be any value. So for instance, cosine of x could take the maximum value, while the sine of y could take the minimum value. So let's just try that. When cosine of x is maximum, then it will be 1. But if sine of y is minimum, then it will be -1. Multiply them both to each other, we'll get -1. And similarly, if we take cosine of x to be minimum and sine of y to be maximum, we'll also get -1. So let's be careful in our reasoning here. So let's think about this logically. So we know that the range of cosine of x is continuous, right? And the range of sine of y is continuous. And we know that every number in between -1 and 1 are some form of proper fraction, like 1/3 or -2/3, right? And we know that when a proper fraction is multiplied by 1 or something that's lesser, we would get something that is lesser than 1 or greater than -1 if we think of it in another way. So if we do that, we find that is either lesser than the maximum value of z can take, which we would find out that's 1, or the minimum value that z could take, which is we find out is -1. So we could say that the range of z is -1 to 1. So we really have to be careful when we find the range of a function. So let's move on to the next function, z equal to ln 1 minus x minus y. So essentially what we have to do is to find out what kind of numbers that we can plug into x and y so that this function makes sense. So in order to do that, we have to think what is defined under ln of some variable, say x. So let p equal to ln x. And this might be confusing right here but this x variable is not the same with this x variable here. So let's just ignore this part and just focus on this. So let's just let p equal to ln x. So we know that the domain for this function is between 0 and infinity. So in essence, we could say that this anything that's inside this ln function must be at least greater than 0, right? So we could just take this variable here, 1 minus x minus y, and say that this is greater than 0, because that will only make sense. So let's just do that. So the domain must be 1 minus x minus y should be greater than 0. And after some algebra, we could get this inequality. But you could also leave it at this way, it doesn't matter. So let's find out the range of z. So let's again consider the simpler case. Let's consider this function p equal ln x here. So if x approaches 0, right, then ln x approaches -infinity. So what we have to do to find the minimum of z is to see if 1 minus x minus y here can approach 0, or if it is bounded by some other value. But notice, as long as x and y don't add up to 1, then the function is defined, right? And remember, x plus y can go as close as to 1, but never gets to 1 because of the density of real numbers, right? So we can safely say that the minimum value of ln 1 minus x minus y, or z, is that there's no minimum value, that it approaches -infinity, right? So again, let's consider the simpler case again. What if x approaches infinity, right? If ln x approaches if x approaches infinity, ln x approaches infinity as well. So to find the max value of z, right, we can find out if 1 minus x minus y is bounded above by some other value. But notice that x and y can take on any negative value, and hence it doesn't get bounded above, because if they are negative, right, then this would be some positive number and it goes on and on, right? So we can also safely say that the max value, that there's no max value for z, that the max value of z only approaches to infinity. So we could say that the range of z is all possible real numbers. Alright, so let's explore the third example. So what is the domain of z right here? Let's examine the simpler case, p equal to the square root of x. And remember, this x right here is not equal to this x. This x is just some dummy variable. So what is the domain of this function? Well, the domain of the function is just 0 to infinity, right? So we could substitute this line, 4 minus x squared minus y squared, to this, to equal to x. So we could say that 4 minus x squared minus y squared is greater or equal to 0, right? Or you could write it in this form so that it can be aesthetically pleasing. Alright, so what about the range? Well, again, let's consider the simpler case where we don't have some extra variables. So for the minimum of square root of x is 0, right? Because square root of 0 is 0. And the maximum value, well, there's no maximum value for this. It goes on to infinity, right? So what we have to find now is that if this range here is bounded below other than the value 0. So what we have to do is to find if this domain here is bounded below by some other value other than 0. Well, the function x squared plus y squared can be equal to 4. So that means that this domain, this line here, 4 minus x squared minus y squared, can indeed be equal to 0. And therefore, this is the minimum value of the range of p, right? And I can say that because this x squared plus y squared is continuous, right? So now we have to find a maximum value. Or in other words, we have to find if it is bounded above by some other value. We find that this is the case, as x squared plus y squared can only be greater or equal to 0. So if x squared plus y squared reaches its minimum value, that is 0, this case it can only be squared 4. Z can only be squared 4, and squared 4 is equal to 2. So the range of z is equal to 0 to 2. So that's all for the domain, for finding the domain of range of a function of two variables.
So after examining the range and domain, let's turn our attention to level curves or contour lines. Actually, level curves and contour lines are another way to represent a function z equal to fxy. And to draw level curves, we first have to let z equal to c, then we can obtain a graph of two variables, or in this case, we call it specifically the level curve. We can obtain more level curves by substituting different c values. So some examples of level curves in real life is the pressure map, which is also called the isobars, as well as the temperature map, which is called the isotherms. So here is an example of a pressure map. This pressure map is pretty simple. We see here along this contour line, the pressure is the same, which is 1036. And along this contour line, the pressure is the same, which is 1032. But as they approaches this region, we can see that the pressure is actually increasing. On the other hand, as we approaches this region, the pressure is decreasing. Here is an example of the temperature map. So for this contour line, the temperature is the same, which is 30 degrees Fahrenheit. And along this contour line, the temperature is the same, which is 35 degrees Fahrenheit. As we approaches this orange region, the temperature is increasing. And as we approaches this purple region, the temperature is decreasing.
Alright, let's learn how to draw some level curves. So let's see this example, z equal to x squared plus y squared. So to draw a level curve, we have to let z equal to some constant c. So let c equal to 1 or 2 or 3 or 4 or 5. So it will form this kind of equation. Once you do that, you just have to graph it just like this. So let's try and get an intuition behind the idea of a level curve. So what exactly does a level curve mean? So I want you to imagine that you live in a completely two-dimensional world, right? So the world is completely flat, and there's no height, there's just width and length. Flatland. So imagine yourself as being this orange right here. So you're kind of bored and running around the field, don't know what to do. And notice that the only way that you could move is leftwards and rightwards and forwards and backwards. And there's no idea of this motion of upward or downward, right? You live in a completely two-dimensional world. So you're running around bored, and then suddenly you hear this voice somehow come from some place that you can't see, right? And this voice utters and says, "Hello, I am an elliptical paraboloid. I'm here visiting your flat world." And this orange just stayed as and terrified and don't know where. He looks around, doesn't see any entity, any friends of his, and he gets afraid. He thinks he's losing his mind. And setting aside this story, right? X squared plus y squared equals to z is this graph, right? Is the elliptical paraboloid, and so you're terrified here, and you don't know what exactly is this voice and who's saying it. So the elliptical paraboloid, this creature, he doesn't like being known as sort of an apparition of some orange's mind. So he wanted to descend into his world, right? He wanted to enter into his two-dimensional world. Now notice that elliptical parabola is a 3D creature, right? So how do you think that the orange would see the elliptical paraboloid? So imagine that this blue plane right here, which is parallel to the XY plane, right, as being your two-dimensional world, as being the flat land, right? And imagine that this elliptical paraboloid descends into this blue flatland, right? So that it intersects this blue plane right here. So what we get is, let me draw back my orange here. So as the elliptical paraboloid, it descends into this orange world, right? The orange could only see this edge, and apparently it came from nowhere. It just sort of appeared, right? And as the elliptical paraboloid continues to descend into the world, right? What you see, what the orange see, is that something gets larger and closer to him. Right. Need my orange back. So the orange is astonished, right? He could only see something gets closer and closer to him, but no matter, but he doesn't know what it is. It just came from somewhere else. So what he decided to do is he asked for some of his friends. He calls out his friends, right? So some of his friends came along. Let's draw some of his friends. So let's say there's another orange here, another orange here. Another orange here. Right. So all of oranges gather around and see this thing. And let's say they have some sort of camera and they took a picture, right? This is what they're gonna sort of, this circle right here is what they're gonna finally, as all of them, let's say there's a lot of oranges here surrounding this circle and all of them taking pictures. And once they combine all of the pictures, they'll get some sort of an idea of this two-dimensional circle, right? So they keep on doing this, they keep taking pictures as this elliptical paraboloid comes down into their world. Right. So what exactly are these pictures that they've collected? Well, it's exactly just the level curve. The pictures that the oranges take is the level curve. So maybe one orange, like once the event taken place, the oranges go home and they start to collect all of this data together, and they try to put it into one picture, so to get something sort of like this, sort of this picture, right? And they couldn't imagine that this is actually the shape in 3D, but they could think of it as they construct it in this way, right? And think about it. If you have all of the contour, all the level curve, which is all of these lines that the oranges take, right? If you've collected all of them for all the planes, for when all the planes intersect this elliptical paraboloid, right? You could actually construct the elliptical paraboloid again if you're a 3D character lah. So if you stack them all together, so that's basically like what a level curve is to an orange. So let's just talk about another example, and maybe you get some better intuition behind this. So here's another example. So given here is the equation z equal x squared minus y squared. So to find the level curve, we first let z equal to some value c. So let c equal to 0 and 1 and 2 and 3 and 4. So we'll get this set of equations. And when we graph it into this, when we graph it together, we'll get something that looks like this. So as you might have known, x squared minus y squared equal to z is a hyperbolic paraboloid, which is this graph right here. So you could think of the level graph as the intersection of this plane, which is parallel to the xy plane, and the surface. So it's the intersection over here, which is represented at this two-dimensional plane. right? So this is the level curve, and you could think of the collection of all of this curve as the level curve in general, as this. So as we continue to collect data, so as the oranges continue to collect the pictures, when they combine them together, you'll get some sort of graph that looks like this. So let's just look at another last example, just to solidify the intuition, right? So let's say it's given that z equal to x squared minus y. So this is an equation that we don't have we didn't learn in our syllabus, in our quadratic surfaces syllabus. So how do we find the level curve, right? So we first let z equal to some value c. So let c equal to 0 or 1 or 2 or 3 or 4, and we'll get this set of equations. Once we get this set of equations, we can plot it in this graph. So we get this level curve in general.
Here comes the hardest part of this presentation, the function of three variables. A function of three variables can be denoted as w equal to f x, y, z. Notice that instead of having level curves, function of three variables has level surfaces. To draw these surfaces, we have to first let w equal to c. Then we can obtain a graph of three variables, or in this case, we call it a level surface. To obtain more level surfaces, we just simply substitute w with different c values. Let's look at an example. So now we have w equal to square root x squared plus y squared plus z squared. The first step we take is to let w equal to c. Then we have square root x squared plus y squared plus z squared equal to c. And with some modification, we can easily get x squared plus y squared plus z squared equal to c squared. The next thing we do is to let c equal to any values, for example 1, 2, and 3. So we have these three equations of spheres. Let's take a look if we have different c values. So remember the analogy we used to describe the contour line, the 2D world? Well, now we want to describe the level surface. We need to extend our world to a three-dimensional world. So now, the 4D beings is going to visit our world now, and as it descends to this 3D world, we start to see a sphere. And as it descends further, we see larger sphere. If we were to take photo of its descent, then we will see what we have is a series of sphere with larger and larger radius. At this stage, our sphere is quite incomplete because of the limit of this cubic confinement. Okay, and collectively, if we were to collect our snapshots together and stack them together, we will have something look like this. Larger sphere enclosing smaller sphere within. So now comes the problem. How do we graph the w function, which is w equal to square root x squared plus y squared plus z squared? Actually, it is impossible for us to imagine the shape of the graph because we are just 3D beings, and the graph lies in a 4-dimensional space. So we can only have these level surfaces of the graph. In conclusion, as 3D beings, we are only able to see the level surfaces of this 4-dimensional object. It's like the shadow of this four-dimensional object being projected into our 3D world, and we can only see its shadow. So in another way, we can only imagine that each sphere that we capture is a point in time, and as time increases, the point increases in size as well. So in physics, actually, we also treat time as the fourth dimension. So thank you for watching our video. Good luck.